All right, class. So now that you are experts, or at least have some ground in variational theory, I'm going to mess with your brain and introduce perturbation theory. So this is our other common method. It's quite different from variational theory. They both have their strengths and their weaknesses, which we'll talk a little bit more about later. So let's think about perturbation theory. So have any of you heard the word perturbation before? Maybe yes, maybe no. It's kind of a weird word. To perturb a system or to perturb something is to alter or to mess with. So literally, this is we're going to mess with things theory of how to approximate an energy result for a system. So we know from thinking about helium, just a simple helium atom, that Schrodinger's equation, H hat psi equals E psi, is not a solvable differential equation for the vast majority of real systems. In fact, the only real system that it's solvable for is the hydrogen atom. But we can totally solve it for particle in a box, harmonic oscillator, rigid rotator, and again the hydrogen atoms. We're going to consider these to be our 4 simple models, right? The most simple we can get. And so here, throughout perturbation theory, whenever we have a superscript 0 that is in parentheses, that's going to denote the model system. So this is, in this case, psi 0 is the wave function of the model system. So whenever you see that superscripted parentheses 0, that means of the model system. And so the first step in perturbation theory is to choose a model that seems similar to our real system. Just like in variational theory, our choice of a trial wave function was critical. Here, in perturbation theory, our choice of a model is critical. So we want to be very careful and very intentional about which model we choose. If we choose to use a particle in a box model for something that doesn't at all resemble a particle in a box, we're going to get a really bad answer. So here it's critical that we think about which model is going to reflect most similarly the system that we're trying to calculate the energy of. So we're going to choose a model, and we know Schrodinger's equation for that model. We know what our Hamiltonian is, so we'll denote that as H hat 0. We know our wave function, psi 0, and we know our energy result, E0. So we know this differential equation. We've already solved it for those real systems. So all of these are in your notes once we choose our system. And so we're going to use this psi 0, this wave function of the model system, as an approximate wave function for our real system. So we're going to keep using it even though we know it's not the right wave function. We're going to assume that it's at least remotely similar enough, right? It's close enough. So we're going to approximate that as the wave function for a real system. And so the next step is going to be to perturb the Hamiltonian to be more real. So in variational theory, we messed with the wave function. In perturbation theory, we're going to mess with the Hamiltonian instead of the wave function. So here we have our real Hamiltonian is H hat. We already said we know our model, right? Our model is H0. We already know this. This is coming from our notes from a previous model system that we've talked about in quantum mechanics. And so we have that H hat 0. And then we can add on terms. So H hat 1 would be our first order perturbation term. H hat 2 would be our second order perturbation term. So we can think of this as like a series in math. So remember from previous math classes, maybe a while ago, perhaps you've completely forgotten, and that's totally fine. Things like Taylor series, Maclaurin series, and all these different series in math, what they really mean is we can take any complex function in math and write it as a series of simpler functions. And the idea is that usually we don't need all those terms. We can truncate that series at some point, and the answer doesn't change much, right? We're not losing much by losing some of the higher order terms. So this is exactly like that. We're saying our operator can be modeled as a series of operators. And usually, only the first couple of terms make a big difference. But the more terms we add, the better we get at modeling our real operator. or in the case of math, usually you're doing functions, so the better you get at modeling your real function. So we're going to treat this like a series, and every term after the zero term is our model, every term after that is a perturbation term or a correction term. So we need to figure out, we know what h hat 0 is. Here's where we would figure out what we want to call h hat 1, or maybe we need an h hat 1 and an h hat 2. And then we're going to, once we figure out what those terms are, we're going to apply our operator, our Hamiltonian h hat, to our wave function, which remember is just the model system wave function, psi 0, to calculate our energy and get our individual correction terms. So if we're calculating our total energy, one way that we can always do this once we have a wave function and a Hamiltonian is take psi 0, and I forgot a 0, sorry about that, let me fix that real quick. Real-time fixing here. Okay, and then we have our Hamiltonian, which we just expressed. Remember, it's our model Hamiltonian plus some other perturbation terms. And we can take this integral over all real space. So Hamiltonian acting on our wave function, our model wave function, multiplied back by our complex conjugate of our model wave function. Integrate over all space, that's always going to give us energy via Schrodinger's equation. But what if we just want individual correction terms? Because remember, we know E0. That just comes from our model. We've already done that math. We don't need to do it again. We can do it again, but we don't need to. So we can also say that E, due to the nature of how we've expressed our Hamiltonian, is E0 plus E1 plus E2 plus E3, where each of those E's corresponds to the Hamiltonian term. So E0 is our model energy result. E1 is our first order correction. E2 is our second order correction, and so on and so forth. And so if we just wanted to solve for, say, some correction term, e to the n, we could integrate over all space by the product of our complex conjugate wave function times our Hamiltonian, and here we're only going to take the n term of our Hamiltonian, so the nth perturbation term, acting on our model wave function. So some notes about perturbation theory before we walk through an example problem. One of the big ways, there's a few big ways that it's different from variational theory, right? Here we're messing with the operator instead of the wave function, but another big thing here is that there's no minimization step in perturbation theory. The energy that we calculate in perturbation theory is not necessarily an upper bound to the real energy. It could be lower than the real energy, equal to the real energy, or higher than the real energy. And we don't really have a way of knowing. Unlike in variational theory, where we always know that the real energy is lower than what we calculate. Another thing to note about perturbation theory is that it's commonly used alongside or mixed with variational theory in several computational methods or theories. So in WebMO, when we're looking at our theories, if we look further down the list of options, remember we have Hartree-Fock is near the top, DFT is somewhere in the middle. Towards the bottom, in the WebMO introduction video, I told you that these were ones we don't normally use. There's MP2 and there's some CCPD. So these MP2 are called Muller-Plesset theory, and CCPD is a coupled cluster theory. It's a specific coupled cluster theory. And so these actually are very complex and time-consuming or expensive computationally calculations where we're actually mixing perturbation theory and variational theory to give us a better answer. And so again, these are much more expensive, and so we don't normally use them because our chemistry server can't handle them very well. Okay, so in the next video that you should watch, so you should do the reading in your book. The next video we're going to work through an example problem together, and then you should work some practice problems. Because again, the way to get good at understanding variational and perturbation theory and their differences is to practice using them.